Today we are very lucky to have one of our participants, Professor Cynthia Chiang, to tell us about her experience about searching this cosmic dawn signal. And Cynthia is actually, she has received her PhD from Caltech, California Institute of Technology, working in the field of cosmic microwave background. And she was a postdoc at the Princeton University before going to the South Pole for a year, wintering over for a telescope called the South Pole Telescope, the SPT telescope, which you might have heard of. And today she's going to tell us, she's now a professor at the UKZN in South Africa, but she's moving actually to McGill University in Canada this year. And she's going to tell us about the searching for cosmic dawn today. Welcome, please.
Well, thanks, Chiang, and thanks so much, everyone, for coming out today to hear me talk about my work. My name is Cynthia, and today I'm going to tell you about an adventure that we've gone on in order to learn about what happened in the universe's distant past. So let me start off by telling you what I do for a living. I'm a cosmologist, and cosmologists are interested in the big picture. So we're interested in the study of the history and evolution and structure of the universe on its largest scales. So the sorts of questions that we like to ask are things like, how and when did the universe begin? What is the fate of the universe? What is the universe made out of? And these sorts of questions are ones that humans have asked as long as we've existed. And to illustrate how old and profound these questions are, I'm showing an engraving that's from the 1800s. So this is quite old. But what's shown here is a curious observer peering out into the heavens and trying to understand what lies beyond. And so even though the artist took some creative license in making this picture, the spirit of this image is actually very similar to what we do today in modern cosmology. And I'm excited to tell you that by doing precision observations and building specialized telescopes, we can actually start to address these questions in scientific and quantitative ways. So that's the story I'm going to tell you today. All right, so the era of modern cosmology began in the 1920s with this man, Edwin Hubble, and he's shown in this picture sitting at his telescope on Mount Wilson. And what Hubble was doing at the time was looking at distant galaxies and looking at how fast they were moving. And he found something pretty remarkable, which is that on average, all of the galaxies appear to be moving away from us. So that's a very strange thing. And he found something even more remarkable, which is that the speed at which they're moving away from us depends on how far away the galaxies are. And so that relationship is encapsulated in this one expression that I have on the slide. Now, I promise this is the only equation I have in my talk. There will be no others, but I'm showing it here because it's a fairly simple one, and it's also really important. So what this equation shows us is that v, the speed at which a galaxy is moving away from us, is equal to just a number, which is 8.0, which turns out to be 70, multiplied by the distance of that galaxy from us. So if we take this relation, which is known as Hubbles Law, and we interpret it, the interpretation is that the universe is expanding and that objects are moving away from us. And furthermore, this equation tells us that the farther an object is from us, the faster away it's moving from us as well. Okay, so this is one important piece of information that I'll ask you to keep in your pockets. And now, in order for you guys to become observational cosmologists for this evening, there are 3 lessons that I need to teach you. So we're going to start off with micro lesson number 1, which is that I need to teach you how we can learn about the universe's past. We don't have a time machine, so we can't do that. We need to find a different way to learn about what happened early in the universe's history. And the way that we do that is by relying on our friend light, the humble photon. And the fact that we're going to rely on here is that light travels at a finite speed. So if there's an object that's emitting light and it's some distance away from us, it takes a finite amount of time for that light to reach us before we can see it. So let's take the sun and the earth as an example. The distance between the sun and the earth is 150 million kilometers, and the speed of light is 300,000 kilometers per second. So if you do the math, then you can calculate that by the time we see sunlight, it's 8 minutes old. So equivalently, it takes 8 minutes for light to travel from the sun to reach us. Okay? So another way of thinking about this is that if somebody just snatched the sun out of the sky right now, made it disappear, we wouldn't know for another 8 minutes, and then we would finally see it. So when we see the sun as it is right now, we are seeing it 8 minutes in the past. Okay? So this is the first take-home message, is that looking at distant objects that are far away from us and emitting light is basically the same as looking back in time. All right, so this is lesson number 1. Now I'm going to move on to micro lesson number 2, which is about hydrogen. Now the reason why I'm focusing on hydrogen is because it turns out most of the universe is comprised of hydrogen, so it's worth spending some time understanding this very simple element in our periodic table. Okay, so a hydrogen consists of 1 proton and 1 electron orbiting around each other, and the proton and electrons have spins associated with them, so just like a top. And it turns out that once in a while, the electron flips upside down, so the spin flips. Okay? And if any of you have ever played with a tippy top before, it's very similar to that. That's the animation that's shown in the lower left. So you can see at the beginning, when you spin the top, it's spinning straight up. But after some time, it flips upside down and starts spinning on its handle instead. These are great toys, so I recommend getting one if you don't have one. But this is very similar to what happens with an electron. Once in a rare while, it flips upside down, much like the tippy top. And there's a remarkable thing that happens when this electron flips upside down, which is that it releases a flash of light. And there's something very special about this light, which is that it has a very specific color or wavelength, and that wavelength is 21 centimeters, or an equivalent frequency of 1.4 gigahertz. All right, so the second take-home message here is that hydrogen essentially glows with this light that is 21 centimeters in wavelength. Okay, so that's micro lesson number 2. Let's move on to the final micro lesson number 3, and this is about how light behaves when it's being emitted from objects that are moving. So the top cartoon shows this orange sphere that's something that's emitting light, and it is moving to the left, so that's away from the observer that's shown on the right-hand side. And what happens in this case is that as this object is moving away, what happens to the light is that the wavelength gets stretched out by the time it reaches the person who's looking at it. And so the color becomes more red in this case, and so we call this phenomenon redshifting, and this comes from the fact that the object is moving away from the observer. Now the opposite effect happens when the object is moving towards the observer, so that's the lower cartoon, and in that case the wavelength of the light gets compressed, or we call that blue shifting in this case. Now the reason why this is important is because remember I mentioned that the universe is expanding and there are distant objects that are moving away from us. And so if we're trying to look at light that's from a very distant part of the universe, on average that stuff is moving away from us, and so we expect that light to be redshifted, or the wavelength to be stretched out by the time it reaches us. Okay, so those are the ends of the 3 tiny lessons that I'm going to teach you to become an observational cosmologist. And now we're going to put this all together, and there's going to be one important punchline that I'll ask you to remember for the rest of the talk. Okay, so let's start with step 1. So as observational cosmologists, we would like to choose how far back in time we want to look, because let's say that there's a particular time in the universe's history that we want to study. So if we select some time in the distant past, because light travels at a finite speed, we can translate that into a distance, so how far away we have to look. Okay? So now with that distance in hand, we can move on to step number 2, which is that Hubble's law tells us that stuff that's at a particular distance from us is moving away with a particular speed. Right? So now we've turned that distance into a speed. And now we can turn that into step 3, which is that if we know that at this particular distance, things are moving away from us with a particular speed, most of that stuff is hydrogen, and it's emitting natural light at 21 centimeter wavelength. But because it's moving away from us, that light is going to be redshifted by the time it gets to us, so its wavelength is stretched out to a particular length that's set by how far back in distance that hydrogen is. All right, so the final punchline, putting this all together, is that we can observe a specific time in the universe's history by literally tuning our radio telescopes to the correct wavelength, right? All right, so that's all you need to know to become an observer. So now that we have this observational tool in our pocket, let's decide what we want to measure. So let's see, this is a picture of a map or a timeline of the universe as we understand it, and there's a lot of stuff in here to measure. So we think that the universe began its lifetime 14 billion years ago in a big explosion called the Big Bang, and the universe has been expanding and cooling ever since then. So as the universe has evolved, there's been a number of important milestones in its history I've outlined here in this cartoon. So starting at 0.4 million years after the Big Bang, the universe cooled enough for the first neutral hydrogen atoms to form, and at this point, the oldest light that we can observe, which is known as the cosmic microwave background, was created at this point in time. So after this era, the universe was filled with neutral hydrogen and was a very dark and boring place for a very long time. And this cosmic dark ages lasted until about 100 million years after the Big Bang, at which point the first stars ignited and dawn emerged in the cosmos. So after this point, as time went on, more structures started to form, including the galaxies and stars that we're familiar with today. And we, as the observers, are sitting at the very center of this picture, looking out and trying to make sense of this strange and wonderful picture. So you can see that there's a lot of interesting stuff in here to measure, but for tonight's story, I'm going to focus on one particular slice of this history, which is the era of cosmic dawn. So this is when we think the first stars ignited in the universe. And I'll mention that these first stars are unlike anything that we've seen today, and we've never seen these before. So this is an undetected and unexplored part of the universe's history. So as cosmologists, we would always like to fill in this picture more and try to understand better what's going on in the distant past. So we think that cosmic dawn occurred between roughly 100 and 400 million years after the Big Bang. And those numbers at first glance may sound very large, so let me help you put this into perspective. If we were to take the entire 14 billion year existence of the universe and compress it down into a human's lifespan, then this era of cosmic dawn would correspond roughly to the first few years of a human's existence. So another way of putting this is, as cosmologists, by studying the era of cosmic dawn, we're basically trying to study the universe when she was a toddler, and she looked very different back then. Okay, so that's the sort of science that we're interested in for tonight. And so now the question is, how are we actually going to observe this period? And the answer is by tuning our radio telescopes to the correct frequencies. So we know that there's hydrogen during this period, and it's emitting this natural 21 centimeter light, but it is redshifted by the time it gets to us. And so we can calculate the appropriate frequencies that we want to look at in order to target this particular slice of the universe's history. And those frequencies are between roughly 50 and 150 megahertz. Okay? So those are numbers that I will ask you to keep in mind. All right, so that's great. All we have to do is build something to measure at these frequencies. So the next question is, great, how do you catch a radio wave? And there is good and bad news here. So the good news is that everyone probably recognizes the megahertz unit I mentioned in the previous slide. And that is because FM radio stations broadcast in these frequencies. So if you want to measure light from the first stars at 100 megahertz, all you have to do is turn on your car radio and done. So everybody here has actually measured light from the first stars, whether you like to or not. And so you might be wondering, well, that's great. Why am I sitting here and why am I not getting my Nobel Prize? And the answer to that, well, that's the bad news, is that the problem is that you can't distinguish the light from the first stars from all of these radio stations that are also blasting at the same frequencies. And so if you tune your radio to 100 megahertz, you can't tell if that light is from the first stars or from your favorite hip hop or country radio station. Right? And the reason why you can't distinguish the signals is because the signal from the first stars is extremely faint. So an analogy here is if you're trying to listen to the radio waves from the first stars, it's like having somebody whisper very quietly into one ear. But if you're trying to do this in a place where you're surrounded by radio stations, that's like having somebody yelling into a megaphone into your other ear. And so you can't really hear that whispering when you're being overwhelmed by that person on the megaphone. Okay, so that's very sad. But there are places in the world where you can get away from radio stations. And so let me show you one of these. This is the Green Bank Observatory in West Virginia, and this is part of the National Radio Quiet Zone. And so we can start our story here and ask, is this place quiet enough to make our measurements? Like, can we actually see the first stars from this location? So the answer, sadly, is not really. So I promised earlier that I'd only have one equation in my talk, and here I'm going to make another promise, is that this is the only type of plot that I'm going to show. But it's an important one, and I'm going to flash this type of plot a couple more times, so I'll ask you to pay attention for just 30 seconds while I explain what exactly is being shown here. So on the horizontal axis is frequency in megahertz. So this is like if you take your car radio and scan across all the stations, you'd be moving back and forth along the horizontal. And then the vertical axis shows you the signal strength that you get from Green Bank in this case, right? So this is if you were tuning your radio from, say, 86 megahertz all the way up to 100 megahertz, that's basically the volume you'd hear as you scan across. So starting at 86 megahertz, you can see it's a pretty quiet location, but as soon as you hit 88 megahertz, boom, there's a huge radio station, and then as you go through all of these frequencies, basically you've got radio stations everywhere. So this is a disaster, because there's way too much FM radio noise in order to be able to see anything from the first stars. So that's very sad. But as scientists, we are stubborn and we don't give up. And there are ways to get even farther away from radio stations than just Green Bank. So West Virginia is not particularly isolated. So a better solution for trying to make this measurement is to try to leave civilization behind. And so this is an example of a real cosmic dawn experiment that is in operation right now. This is the Edges telescope, and it's operating in the middle of nowhere in the desert in Western Australia. And unfortunately, this picture doesn't really do it justice, but if you go on Google Earth and take a look at this region and zoom out, you will see that there's hundreds of miles of nothingness out there. So this is a really isolated location that's really far away from radio stations. So now we can ask the question again, is this place quiet enough to maybe get a glimpse of the first stars? And the answer is, yeah, this is a lot better than Green Bank. And so this is a picture, once again, of the sort of strength that you see as you tune your car radio back and forth. And you can see there's a couple of stations that make it through, but generally speaking, this is a really quiet location. And so this is an excellent place to observe, and this experiment has been operating for a while now. So I'm not sure if Judd Bowman is still here, but he was speaking to you guys during the Physics Cafe, and this is his project. So I encourage you, if you have questions about this experiment, to talk to him afterwards. It's a great experiment. But today, I'm not going to talk so much about this experiment. I'm going to focus more on one that I've been part of, and I'm going to tell you the story of this guy, which is called PRIZM, and it stands for Probing Radio Intensity at High Z from Marion. So before I tell you about the location and where we've sent off this experiment, I want to tell you a little bit about how we build these telescopes. Because probably by now you've noticed that this experiment and the Edges experiment, they don't look anything like telescopes as most people understand them. So when you think of telescopes, you probably think of Hubble or the ground-based telescopes that are in the huge domes looking out. And the reason why these things look so different is because they are highly specialized instruments that we design and build ourselves in order to do this science. So you can't go to a store and say, I would like one cosmic dawn telescope, please. That's not going to work. So because we have a very specific science goal in mind, we design our instrumentation ourselves in order to make this. And of course, and I say we, it's not really me. I just do paperwork these days. The real work is done by the students, and so I want to say a little bit about them. So this is the dream team. These are the guys who make it work, except for there's one other faculty member in there, but he doesn't count. It's the students who really make it all work. And these are the guys who design and build everything. So I just want to show you some examples of kind of the day-to-day life in a student. So this is my PhD student, Liju Philip, and he's the one who designed and built the antenna structure and the mounting scheme for this. And so you can see that when he started designing this, he started off with a paper model that was built out of cardboard and bendy straws, so that's in the upper right. And then eventually, once he was happy with that, he turned it into a mechanical drawing and then worked with a local fabrication company in order to turn it into reality. And all of this was done by a student. So we don't have professional engineers, we just kind of hack it together ourselves. But it's a tremendous amount of fun. And then another example is, this is actually an undergraduate student who was working with me at the time, Austin Gumba, he's on the upper right. And he designed and built the enclosure for our readout electronics. He had never done mechanical design before, but just taught himself and figured out everything. And now this is a working part of our system, and it works great. So once again, huge shout out to the students, because they are the ones who make this happen and who make it all work. All right, so that's kind of the philosophy of why the instrument looks the way it does. And now I'm going to move on to talking about where we set up this instrument, because like I mentioned before, our goal is to leave civilization behind, and so this is where we set up our telescope. It's a tiny island in the middle of nowhere called Marion, and it's about halfway between South Africa and Antarctica. It's about 2,000 kilometers away from anything else. So in the lower right, you can see what the island looks like topographically. To give you a sense of scale, the east-west dimension is about 25 kilometers. So there are people who do regular circuits around the island, walking around the circumference. If you're really in shape, which is not me, the really in shape people can do it in about a day. I've never attempted it myself. So there is a research base that's located on the northeast corner of the island, and that's where all the logistics operate out of. And that base is shown in the upper right-hand picture. All right, so since most people don't get a chance to go to this island, I'm going to take you on a virtual trip and show you what our deployment was like last year. So that's when we sent down our telescope last April. And I'm just going to show you some slides that illustrate what our journey was like and what it's like to set up one of these telescopes. So our journey started in April last year, and we departed from Cape Town. Access to the island is via ship, and so this is a picture of our ride. This is the S.A. Agulhas 2. It's an icebreaker. And this is the deploying team. So it's myself and 3 students, collectively known as Team Awesome. So it's Redima Nunhoki, Heiko Helgendorf, and Litu Philip. All 3 of them, they are the ones who made this all work. And here's a picture of them being very excited to leave land behind. So we were delayed in the harbor for a couple of days, but we finally pulled out on April 8th. And this is a picture of us leaving Cape Town behind. So this is the harbor mouth. You can just barely see there's the green and the red lights. So red for port, green for starboard. And then that's the pilot ship that's navigating us out of the harbor. So by the morning, there was no more sight of land and this just open ocean all around. It's really quite lovely out there, except for the 5-10 meter swells, but that's a side note. And then a few days later, we arrived at the base. And so this is what it looks like from the ship as we were out in the water. So you can see the new base is on the right-hand side and the old abandoned base is on the left-hand side. Now, as we were sitting out in the water waiting for transport, there were king penguins swimming around, all wondering what this mysterious red iceberg is and trying to see what's on there. The wildlife is really a lot of fun. It's a good perk of the job. Now, transport to the island is via helicopter because there's no place on the island for the ship to dock. And so this is us waiting for transport. This is a Bell 412 EP. It's an absolutely stunning machine. And so we got to ride over, and this is an aerial view of the base as we were flying from the ship over to the island. And then this is our team. Come on, it's gonna win, yep. This is our team finally on the island side with the ship in the distance and the helicopter still buzzing around overhead. Okay, so let me pause here and tell you a little bit about what life at the base is like. In a nutshell, it is cold and wet and windy and exhausting. So I'll give you a few fun facts. So during April, which is when we were there, the average temperature is about 43 degrees Fahrenheit or 6 degrees centigrade. And it's pretty constant year-round because the weather is moderated by the ocean. So it gets a little bit below freezing sometimes, but not dramatically so. It's a very, very windy place because the island is situated right in the roaring 40s. So the average wind speed there is about 14 knots, and the maximum sustained wind speed can get up to 50 knots. I've experienced wind gusts up to 80 and 90. It's not a lot of fun when that happens. So it's a windy environment. It's also one of the rainiest places on Earth. So on average, there's about 200 millimeters of rain per month. And then it's also a very isolated location. So during this takeover period, when the ship returns for a few weeks and there's the relief voyage, there's about 70 people running around. And then when the ship leaves, it leaves behind 22 poor souls who take care of the base and everything during the winter. So I'll come back to that point later on. All right. So after we arrived at the base, the first thing that we had to do was figure out where to set up our telescope, because we had to figure out where a nice patch of land was that was suitably flat, not too far from the base, but not too close either. And so this is a picture of our team going around with an antenna and trying to figure out if there was an appropriately quiet place to set things up. Okay, and so this is where we ended up. So this is an aerial view of this portion of the island. And the base is that little yellow dot on the upper right-hand corner. And then where we set up our telescope site is behind the nearest hill, so about 4 kilometers away. Now, the reason why we set up so far away is because if there are people wandering around the base with handheld radios and such, we don't want any of that contaminating our antennas. And so there's a trade-off because we want to go as far away from the base as we can in order to reduce any potential contamination from people chatting on their walkie-talkies. But at the same time, we don't want it to be so far away that it's extremely painful to hike out there. So this is kind of the compromise that we ended up with. So 4 kilometers, it was a 1-hour hike one way. What this map doesn't really capture is the realities of hiking on Marion Island. So let me show you what that's like. Like I said, Marion is a very rainy place, and so the island is largely covered with mires or swamp. And so when you're walking around, sometimes a foot goes in, sometimes a leg goes in, and you never really know until it happens. And then sometimes it's hard to get out. So that picture in the background shows Redima encountering her first mire. So that was a good day. The other thing that makes hiking difficult on the island is that there are patches of black lava rocks, and so it's really easy to twist your ankles on those and fall over and cut your hand open, so that makes things exciting as well. And to make things even worse, you're issued gum boots to hike around the island, which are not particularly ankle or knee friendly, and so everyone's clomping around in these boots that are way too big for them and don't offer a whole lot of support, meanwhile trying to not fall into the mires and not trip over the lava rocks. And then at the same time, sometimes you're blasted by 80-knot wind gusts and horizontal rain and ice pellets. So it can get pretty miserable sometimes, but it's all for the science, and so we smile and try to get through it anyway. All right, so back to the timeline. After we finally selected our site, after a few days, we did our final tests at the base and then did our final packing of the container. So the right-hand picture shows Heiko looking very concerned about whether or not we have all of our stuff packed. It's pretty nerve-wracking to convince yourself that you're actually ready to have all of your cargo slung out into the middle of nowhere where you don't have a whole lot of support and help if something goes wrong. But eventually we convinced ourselves that we were ready, and so then we called up our friends on the helicopter team to assist us with cargo transport, and so these are the couple of birds on the island. And then this is a shot of the inside of the helicopter as they were delivering us as the humans first, and then they came back to the base to get the cargo. And then this is a shot of the containers being delivered to our observing site, and you can see that we are 4 kilometers away from the base. So for those of you who were here before the lecture started, this is a still photo from the video that was showing that was footage of all of the slinging happening during this time. All right, so the helicopter team dropped off our cargo and then said goodbye and abandoned us and went back to the base. And so we got to work right away and we unpacked our stuff and started setting things up. All right, so we started off by assembling the smaller of the 2 antennas, and this is a picture of one of the students putting all the stuff together. I should mention that she's a data analysis expert, and so her PhD has been focused on computer programming, but she really wanted to turn nuts and bolts, and so she became a hardware expert along with us. And then, remarkably, everything worked on the first try, and we were able to get first light the day after. And so that's the picture that's shown on this laptop, the kind of psychedelic colors there. Now, I have to pause and say that, for somebody looking at these random colors, it really doesn't look like much. But for a person who is putting together an instrument, there are no words to describe the amount of relief that comes when you see a first light picture like this, because what it means is that all of the components work and they all talk to each other, and so you have end-to-end communications through the entire systems, and nothing is broken yet. So that's a huge sign of relief when everything is working and you have first light, even though it doesn't really look like much to write home about. So I can assure you the students were very happy at this point, even though they look cold and miserable in the picture. So after we assembled that first antenna, then we assembled the second antenna, and all systems are ready to go at this point. So at this point, I forgot to mention that the time on the island is extremely limited. So access is only once per year by the ship, and then once we're there, we have only 3 weeks to do everything. And so at this point, by the time we had everything set up, we were about halfway through that 3-week period, and we only had 1.5 weeks left in order to make everything fully robust in order to leave behind for the winter. So we kind of scrambled to learn our system and to understand everything, and that took some time. So one of the things that we had to learn about on the island was that the whole place is infested by mice. It's an invasive species, and so and they cause a lot of problems. They cause a lot of damage to the wildlife. It's all very sad, so I won't tell you the stories there. They also cause a lot of damage to our electronics, and so it took us a while to understand what the mice like to eat, when they like to eat, and kind of a little bit of mouse psychology. And so after a little bit of back and forth and trying to figure out how to mouse-proof our system, and after losing a couple of wires here and there and patching those up, we eventually won. So an example of how we mouse-proofed is, it's a little bit hard to see in this picture, but those cables running into the container where our electronics are housed, they're all wrapped in wire mesh cloth so that the mice can't chew through that, and that seemed to work. So in order to test that concept, I made a little wire mesh bag and put a cookie inside and then sealed it up and then left it outside overnight. And the next morning, there was evidence of mice being around the area. There were mouse poops everywhere, but the cookie was intact. So we knew that this would be a suitable protection for our electronics as well. Okay, so that was mouse proofing and robustifying, which took about a week or so. And then we took one afternoon off to go see the wildlife on the island. It really is a lovely place. There are 4 varieties of penguins, and there's albatrosses all over the hills. So, like I said, it's a nice perk of the job. All right, then the last day of summer operations was May 4th, and then we left the island on May 5th, and that was it. All right. So then, when we left the island, we left one team member behind, and that is Kagiso Malepe, who is an engineer for the South African Space Agency, and he is the one who is taking care of our experiment over the winter. So by the time all is said and done, he will have been there for 13 months, and he is a rock star. So he trudges out those 4 kilometers to our telescope every week or so. He fixes all the broken things for us, so he gets all of the credit for keeping our experiment happy. Right, so that's the story of our deployment and how we set up our experiment on the island. So at this point, you might be wondering, was it all worth it? So how radio quiet is our new site? And so the answer is that it looks pretty good so far. So this is, once again, the plot that I mentioned before. And just to give you some sense of perspective, I have 2 sets of data plotted here. So one in the black is data that's taken from a desert in South Africa that's also a very radio quiet location where a bunch of telescopes are being installed. But you can see that in this particular frequency range, you can still see a lot of the radio stations percolating through. Now, if you compare that to Marion, our island site in red, you can see that there is nothing visible by eye. And so it is beautifully silent on this island, and so we think that we may have a chance of seeing the first stars from this location as well. So we haven't seen the signal yet. It's a tiny signal that's going to be buried in the noise somewhere here, but we are continuing with our observations right now and our analyses. And so I don't have results to show you today, but we are looking for this signal. Edges is looking for this signal, and several other experiments are. And I think there's going to be a lot of new and exciting news that's coming up soon, so stay tuned for updates. But this is kind of where that story ends for today. So I'm going to end just by saying that I hope I've convinced you that radio astronomy lets us explore uncharted territory in the universe's history. And there's a handful of new experiments out there that are searching for the birth of the first stars in this period known as cosmic dawn. And we haven't seen those first stars yet, but we're looking very hard, and we hope that we will soon be able to see this new period of the universe's history that no one's ever been able to see before. But the most important point that I hope I've convinced you of today is that this work is tremendously fun. And so we get to think about big science questions. And in order to answer those questions, in order to do that, we build and we make our own toys, and we get to go on these wacky adventures. And at the end of it, we get paid for it as well. So as a job, I really couldn't ask for anything more. So I'm going to leave my story there and end, and I'll take questions. Thank you.
Thank you, Cynthia, for sharing this venture with us. Yes, so question?
Yeah. Is there any easy way for you to explain to us how those devices are actually measuring what you're trying to measure? Because looking at them, you can't tell.
Yeah, that's an excellent question. So the question was, how does the device actually measure the signal? And the answer is that, so the telescopes that we have are antennas. So they're very much like your TV antenna. And these antennas are designed to pick up electromagnetic waves. So the light that's coming from the first stars is just a wave that makes electrons move back and forth in the wires. And so then you can detect this with various amplifiers and electronics on the other end. But that's essentially how it works.
I know I'm going to get his name wrong, but Koigo?
Oh, Kagiso?
Kagiso?
Yeah.
Yeah. I noticed he designed the prism as a shape like a flower instead of a traditional dish.
Right.
Why was that?
So that was actually Liju who was doing the antenna.
Liju.
Yeah, no, that's fine. So no, that's an excellent question as well, which is why this improbable shape for the antenna, because it looks kind of like a flower. And actually it was kind of named after that. They're called hibiscus antennas. So the answer there is the simplest antenna that you can build is just kind of 2 arms sticking out. So that's called a dipole dipole because you have one arm on one side and one arm on the other side, and you look for the electrons moving back and forth in these wires. But you can change this design a little bit to make it receive more than one frequency. So a dipole is usually good at, is optimized for generally a very narrow range of frequencies, but we'd like to see more with our experiment so that we can see broader features. And so you can tweak the design of a simple dipole so that you can make it more broadband. And so there's different ways to optimize it. And so one example is making 4 squares, or a couple of squares instead of a dipole. And then for our particular antenna, the reason why the squares turned into diamonds and then had all those angles added to them is because the response, or the way it behaves on the sky, is a little bit nicer according to the simulations that we ran. But it's kind of hard to come up with an intuitive explanation for how the design evolved that way. It does come from simulations. I have to be honest, I don't have intuition for how it ends up that way as well, but the computer tells us that it works.
When you get the data for the first stars, will you be able to construct an image for it, and how do you hypothesize the stars will appear?
Okay, that's a wonderful question, which is, can we actually image these first stars? And so this is a part of the story that I glossed over, which is that with our current instrument, we can't really do that because we're looking for kind of an average effect of the stars overall. So we're not looking for individual stars out there, but rather how they affect the temperature history of the universe. And so we're basically using our antennas as thermometers to understand how the temperature evolved with time, or equivalently with frequency. So unfortunately, with our current system, we can't see individual stars, but we can see the effect that they had on the thermal history of the universe. Now, for future generations of experiments, we're going to try to look in more detail to see if there's variations across the sky, but we're not there yet. We haven't even seen the average effect, so one step at a time, but we hope to get there eventually in the future.
On your previous graph of signal strength, it looked at about 125 megahertz that your graph actually dipped below 0?
You noticed that. Yeah, so that actually has a technical answer to it. The question was that weird dip at 125 megahertz where the line drops down a little bit. That is the frequency where our electronics are clocked. And so that's an artifact of our system, but it's known and we can just cut that out and we don't have to worry about it. But you have a very good eye, you noticed that.
Looking at the history with Hubble, Edwin Hubble,
yeah,
and using light, visible light, and calculating galaxy distances, they're using the Cepheid and the supernova brightness. Mm-hmm. But you're saying from your graphs that you're actually able to calculate distance from frequency shift. Mm-hmm. Is that right?
Yeah, that's right. And so that comes from the fact that hydrogen is emitting this 21 centimeter wavelength radiation, and it's very narrow in frequency. And so, so when you have hydrogen at different distances from us, it's moving away at different speeds. And so that means that that wavelength is redshifted very precisely to different wavelengths. And so that's why I was saying before that if you select a particular frequency, then that corresponds to a particular distance or speed at which the hydrogen is moving away from us.
Does this all correlate then with the magnitude, with the Cepheid process or the supernova brightness process? Do the two agree with each other?
Not, I think the two are...
Does one reinforce the other?
I'm sorry, say that again?
Or does this technique reinforce the original thought of the magnitude brightness?
So the measurements that you're talking about are kind of, they're the foundations of the cosmic distance ladder. Right. I am not sure, I don't think that these the measurements of 21 centimeter have been used for that. Okay. I'm not sure how they would be. But,
thank you.
Yeah.
Hi, so I saw that when there were the satellites on the ground that there was a mesh underneath them. What is that mesh for?
All right, that's another fantastic question. So this is about the mesh that's shown underneath our antennas. There's a lot of good people with sharp eyes in the audience today. So remember that our antennas are basically dipoles, so there's two arms. And so the radiation pattern from a dipole like this is, okay, let me back up 1 second, is that, when you talk about an antenna, the way that it receives radiation is exactly the same way as if you were to transmit from there. And so it's easier to think about this in the transmitting sense. So if you have a dipole and you're transmitting out from it, it turns out that the power that you send out is symmetric, and it kind of looks like a donut, right? And so what we want to do with our donut to receive power is we don't want part of that donut looking into the ground. We want to focus all of it onto the sky instead. So if we had just a dipole by itself, it would be sensitive to power in all sorts of directions. And the purpose of that mesh underneath the dipole is to act as essentially a sort of mirror to reflect part of the response of our antenna back onto the sky and fold it upwards so that we get more sensitivity looking up. That was an excellent question.
What is the current thinking as to what these first stars should look like?
They look very different from anything that we see today. So there's actually a very wide spread of theories out there, and I'm actually not an expert on this. But if you look at the sort of models that, and the kind of signals that they're predicted to show in the data, the models are all over the place. And so we really know very little about these first stars. And there's a lot of other speculative ideas out there about what could be floating around in the early universe. So I think the quick answer is we have no idea. And so that's why we want to make the measurement.
Right. Well, we would like to thank, another question?
Just real quick, so are you capturing data in real time, or are you logging it and then going to bring it back physically?
Yeah.
Are you going to set up more of these so that you set up an interferometer?
Yeah, so 2 excellent questions. The first is what happens to the data. So that's another fun thing to answer, is that our data rate is very slow. So we're just taking a handful of numbers every few seconds or so. So it turns out that our electronics are controlled by a Raspberry Pi, if anyone in the audience has ever played with one of these. And our data rate is low enough that we can just write the data to the SD card on the Pi and call it a day. So unfortunately, the sad news is that there's not a great Ethernet connection between the island and the mainland. So we can ask Kagiso to send back diagnostic plots, but we can't send back all of our data. So we can get little chunks to check on things, but we will have to physically retrieve the data at the end of the day when we go back in April. So that's the answer to the first question. The second question was, are we going to build more of these? And yes, actually, we just had our observing program renewed for another 3 years. And so the plan is to install more antennas and also at lower frequencies so that we can explore more parts of the universe's history. And for these new antennas, the hope is eventually, after a couple of years, to develop them so that we can do proper interferometry with these from various stations located around the island. But we have a lot of work ahead of us, so that's the dream plan.
You said that the first stars would look very different, and then you said that you have no idea what they will look like.
Yeah.
How do you know they will be very different? Or what do you know that leads you to believe they'll be very different in some unique way?
That's because I talk to my theorist friends, and they tell me this. So there are people in the audience who are much better equipped to answer your question than I am, unfortunately. So I am mostly an instrument builder, and I try to design the experiments. So unfortunately, I don't have a whole lot of wisdom to offer on that front. But there are many people in the audience who can. So I'll defer to their expertise.
Okay to take one more question?
Yeah.
Okay.
On average, how long does it take for you to design the experiments and the satellites, mainly because it seems like it could take years on average, so.
Yeah, you have very good intuition there. So the question is, how long does it take to design one of these experiments and to see it through to completion? And the answer varies. So the scale of this particular experiment for PRIZM is small enough that it fits within a PhD student's lifetime. So yeah. So Liju, lead student on this project, he actually was there for the very beginning of it. So he designed and built everything from scratch, and now he will soon have the first data in hand, and we'll be able to analyze it as well. So that time frame is a few years, but depending on what exactly you're building, there are, of course, other experiments out there, specialized cosmology experiments that can take many more years to develop. There's other experiments that I've worked on that take 10+ years to build from start to finish and take much larger teams. So it depends entirely on the scale of the project and what science you're trying to achieve. It can be a wide variety of things, but the good news is that whatever you're interested in, there's probably something out there that fits you. So yeah, lots of fun opportunities.
All right, thank you all very much. So let's thank Professor Cynthia Chiang again. Thank you.